Hi, I'm Karyn creator of Nifty Numbers Family Math Night, and in this video I'm going to share with you a collaborative project that I did at my last Family Math Night event where we created a large fractal called the Sierpinski triangle, and you can see the results of that behind me. But if you've seen my video on the Sierpinski pyramid, then you're familiar with fractals. But basically fractals are complex shapes that look the same far away as they do close up. And that's because they're made up of repeating patterns that are self-similar. In other words, they're made up, the large version is made up of smaller and smaller versions of itself. So if we look at the Sierpinski triangle here, you can see, and I tried to get the whole triangle in the video shot, but the tip is missing. But you can see that this is a triangle. And this large triangle is made up of three smaller versions, self-similar versions of itself, and each one of those is made up of three smaller versions of itself, and each one of those is made up of three smaller versions of itself, and each one of those is made up of three smaller versions of itself, and so on and so on and so on. So you can see the self-similarity there. So I'm going to describe how we did that project, and then I'm going to give you a couple of different levels that you can do with the project as well. And then we're going to talk a little bit about Benoit Mandelbrot and some more fractals. And we're going to tie fractals into this super important little thing that we have in our lives called the cell phone. Okay, so first, the activity. You're going to need a whole bunch of different colored pens or crayons or colored pencils. You're going to need scissors. And you're going to need copies of the activity sheet, the Sierpinski triangle fractal activity. And you can find this and all of the activity sheets as PDFs on our website, www.familymathnight.com, under the resources section. Okay, so when I make my copies, you can make it on regular paper. I like to make mine on cardstock, which is a little bit easier to work with when you go to create the triangle. Oh, and the other thing that you'll need obviously is tape to put up the individual triangles. Okay, but if you don't have cardstock, that's okay. It can be done. This particular activity can be done on regular paper as well. So what they're going to do, and the instructions are on there, but what they're going to do is they're going to color in all the inverted triangles, so the upside down triangles. Now I say upside down triangles because we know that a triangle is a triangle is a triangle, right? No matter the orientation of the triangle, it is still a triangle. Well, kids are so used to seeing triangles in this orientation that they end up calling this an upside down triangle, right? But it's not. The orientation doesn't matter. But for the purpose of this activity, I am going to call these upside down triangles the inverted triangles because it makes it easier to do the activity. And basically that's it. They just color in all the inverted triangles, and then they cut that out. And when it's done, it's going to look something like this. And then they're going to give this to the station facilitator, and the station facilitator is going to add it to the Sierpinski triangle that they're building on the wall. Super fun and super cool. Okay, so at our Family Math Night events, all of our kits come leveled. Okay, each station comes leveled, beginning, intermediate, and advanced. Now this activity here, I would consider the beginning level. If you want to divide this into the beginning, intermediate, and advanced levels, then the intermediate level is going to look like this. Okay, so you're going to get this grid of triangles, and the directions are on there, but basically what they're going to do, and for this part that you're going to need rulers too. And if you're going to do the levels, I would get rulers that have centimeters because the advanced activity you're going to be working in centimeters. Okay, so so for the intermediate part, they're going to create an equilateral triangle. So now we've got some great geometry vocabulary in there, right? All sides are equal. So an equilateral triangle with a unit length of 8. And each unit is one side of the triangle there. And it turns out that you can only fit, the largest triangle that you can make has 8 units in length. Okay, so then they're going to continue to follow the directions. They're going to find the midpoints of that and then connect those midpoints and so forth. And when it's done, it'll look something like this. Now, you can take this to the next level. You can take all of these triangles here that are not colored in. You can find the midpoints of those. So now we're getting into a little fraction work, because if this is length here is 1, then in between there, that midpoint's that's going to make this half and that half. So you find the midpoints of these, and then they connect those. So you, like I said, you can go down one more level where they create little triangles in all of these, okay? But that's entirely up to you. And again, they would cut this out, hand it to the station facilitator, and add it to the one that's growing on the wall. Okay, now for the advanced activity, I'm going to have you look at this triangle a little differently. It's going to make sense in just a minute when I talk about the advanced activity. But I want you to look at this triangle and this black part here. Let's say I colored that in black, and I'm taking this and I'm removing it. So that part is gone. Okay, and then the next iteration or the next step would be to find the midpoints of this triangle here and then create this center one. Obviously I've got it created. Take that and remove it. So if you can look at this, like all of those black pieces are missing from the triangle. That's going to help this advanced activity. Another way to show that is, okay, I've got it here on this poster, but here's our original triangle. Okay, now create that center part and get rid of it. Okay, and now you're left with how many triangles? 1, 2, 3. You do that with the remaining triangles. Okay, you connect the midpoints, you get rid of it. How many are you left with? 9, and so forth. Okay, and while I'm at it, since I have this out, here's another very famous fractal called the Coke snowflake right there. Okay, and when I'm introducing self-similarity to students, I do it using pattern blocks. So there's another idea. Okay, but back to our advanced activity. So we have the idea of taking that and getting rid of that middle part. Okay, so this is the activity sheet that goes along with the advanced activity. And you can see here that there's just one big triangle on here. So we're going to put these kids to work. This is where the centimeter ruler comes in. They're going to need to find the midpoint of this. And before we even get to that, this triangle here is already, you can see that there's a table down here, is already on filled in on this table here, but I haven't done anything yet, right? So this is my 0 iteration, my 0 step. I haven't done anything, and what do you see? You see one triangle, and there it is in the table. Now the next thing that I'm going to do is find the midpoints, and that's why they need to use centimeters, because this is measured in centimeters. When they find that midpoint, the midpoints, then they're going to connect it. And I have not finished this yet, but it will begin to look like this. So you can see I connected those midpoints. Okay, so that was my first iteration of my first step. So how many triangles have I now created? Now, if you really look at this, there are 4 triangles here, right? 1, 2, 3, and 4, because we're including that inverted one. That's why I did that earlier activity with you where I said get rid of it, because we're not going to be using this piece to continue our fractal. Okay, so that's why we're not going to include that when we fill in the table. So there are 1, 2, 3 triangles left. And then you'll do the same thing with those 3 leftover. Then you color this in, and you do the same with those leftovers. You find the midpoints, okay, and you draw those, that center inverted triangle, right, and you get rid of it. And then what are you left with? And you begin to fill in the table. So that second iteration is going to have 9 triangles, and the third iteration is going to have 27 triangles. And now you can start to see that pattern, right? Because that's what we do in math. We look for patterns, and then you'll discuss the patterns. And they'll notice that, and these are your upper elementary students, that that 1 is 3 to the 0 power, and then we've got 3 to the 1 power, and 3 to the second power, and so forth and so forth. Okay, on here they can make a prediction then. But if you were going to write an equation for this, we know that this column here, okay, is our x and this is our y. The equation here would be y equals 3 to the x power, and the x is the iteration of the step that they're on. Okay, if you want to take it to that level. Now, what I would do at my next family math night is actually create a large table like this, and I would have more rows on it, and we could begin to fill it in as the table was being generated, and that way we can tie the numbers into the activity that we're doing. Okay, so that's the advanced, and again, they would cut this out, and of course all of these triangles at the beginning, the intermediate, and the advanced level are the same size triangle, right? Because when you cut them out, you want them to be able to fit nicely on the large one. Okay, so before I move on to Benoit Mandelbrot, I just want to share with you at all of my family math night events, or my recent ones, I've done a "What do you notice" poster. And it's an open-ended question, which I love because it allows kids and parents to think outside the box. And so at a recent one, I created this, and you can see here that this is a fractal. There's self-similarity in here. So it's totally open-ended. They could notice something as simple as, gee, it's made up of squares, or they could start getting into the numbers and maybe notice the powers or whatever they want to do with that. They write their little observation on a Post-it, and then they put it on there. So super fun to do this, but I wanted to share that because that's another very famous and popular fractal. Okay, now I'm going to talk about Benoit Mandelbrot, the father of fractal geometry and the creator of this new area of study, and also the guy who came up with the name fractal, and that would make sense since he discovered fractals. But he discovered them when he was studying the British coastline, and what he realized was that the large coastline was actually made up of smaller and smaller versions of itself. So this idea of self-similarity that we've been talking about. But then he started to notice it in lots of other areas of nature. So for example, the branches of trees, or the leaves of ferns, or the way that lightning branches out when it comes down to earth, or broccoli, and lots of other areas. And he realized that out of this seemingly chaotic and complex situations actually arose order and regularity and predictability. And so from that came chaos theory. So order from chaos. But he also realized something else that nature had figured out eons ago, and that is that fractals are super, super efficient. So for example, fractals allow plants to maximize their exposure to sunlight, and fractals allow the cardiovascular system to deliver oxygen to all parts of the body in the most efficient way possible. So nature has a way of teaching us these things, and then we use them to benefit ourselves. For example, think Velcro. So Velcro was invented because a Swiss engineer who was annoyed at having to pull off little burrs from the fur of his dog every time they went out into the woods, took one of those little burrs, looked at it under a microscope, saw how it worked, and invented Velcro. And who doesn't use Velcro, right? Well, the same thing happened with fractals. And to get to that part of the story, I need to go back to the late 80s, and a man named Nathan Cohen, who at the time was a professor at Boston University and having problems with his landlord because his landlord wouldn't let him put an antenna outside of his apartment. Well, around that time, Professor Cohen went to see Benoit Mandelbrot talk about these fractals. And he started to think about this idea of fractals, and he wondered, what if I created an antenna in the shape of a fractal? So he took a wire and he did that, and lo and behold, it worked beautifully. In fact, it didn't even need to be really large, so it kind of solved his problem with his landlord. But that brings us to present day and our cell phones. Okay, so our cell phones have in them something called fractal antennas. And these fractal antennas allow our cell phones to access a wide range of frequencies, so our Wi-Fi and Bluetooth and so forth, without having to have a whole bunch of antennas sticking off of our cell phone. So it eliminated the whole antenna part of it. And those antennas could be super, super small and still work efficiently. Okay. So it's really cool to think that a random topic in math, fractals, and this fractal activity, the Sierpinski triangles, how those connect to, and it's great to show kids and parents how this connects to something that's relevant to their lives and super important in their lives. You know, their cell phones are really important. It makes math meaningful and valuable and very, very cool. So have fun.